We'll continue the problem. See, next step is selection of the oil. Third step, which type of oil we are going to calculate. For that, we are assuming operating temperature. Since we don't know in the question, they're not given the operating temperature. So we are going to assume the operating temperature T0 is equal to 65 degree Celsius. Now, from the figure 24.2b, based on the operating temperature and based upon the neta we'll get in the first step, we are going to calculate the type of the oil. Now if you see the figure 24.2b, so here we are having the type of the oil, that is SAE 10, 20, 30, 40, 50, 60 like that, and here we are having the absolute viscosity, and here we are having the operating temperature. Now we are having the operating temperature is equal to 65 degrees Celsius, something we are assume. So we are assume operating temperature is equal to 65 degree and neta is equal to 60. So if you refer that figure, so here we are somewhere we will get in between 60 to 70, we will get somewhere 65 we will get, and absolute viscosity we are having 60. And so we are having 60. So then if you go, then we will get the SAE 60, that is the type of the oil we will get, that is nothing but SAE 60. Now from the table 24.1, next we have to see the table number 24.1. So here we are having table number 24.1. Now see, for SAE 60, we are having number is equal to H. So this SAE type of 60 it is used for aeroplane oils. So the number is equal to H. So we will get the SAE 60 is H oil. And sure. Now whatever the oil we have selected, it is right or not. Now we are going to check. That is nothing but check for the oil. Now we are going to take bearing modulus S double dash calculated is equal to neta n dash by P. We know neta. We can calculate n dash, that is nothing but n divided by 60. We have taken P is equal to 2 into 10 to the power of 6. We will get bearing modulus. Calculated bearing modulus is equal to 100 into 10 to the power of minus 9. Now this calculated bearing modulus should be greater than the bearing modulus obtained from the first table. See, from first table we got bearing modulus is 48.4 into 10 to the power of 9. This bearing modulus is less than the calculated, hence thick film lubrication is possible and the selected oil is suitable. So in this way we are going to select, we are going to check whether the selected oil is suitable or not. So this is the third step. Next step is heat generated. So we are going to calculate how much amount of heat is generated by using the formula Hg is equal to mu PLV. That we can write it as mu W into V. So here we can calculate mu by using the formula, or we can calculate mu by using the figure. So now if you see the figure number 24.20, if you see the figure number 24.20, by using this figure we can calculate mu. See, if you go to figure number 24.20, see, this is the figure 24.20. Here in the x-axis we are having bearing characteristic number S. Y-axis we are having the coefficient of friction variable, that is equal to mu by xi, and number of curves we are having L by D. So in order to calculate this y-axis, first we have to calculate x-axis and the L by D. So first we will calculate S, that is nothing but x-axis. We know the formula S is equal to neta n dash by P into 1 by xi square. Substitute neta n dash P into 1 by xi square. So we will get S is equal to 0.1235, and L by D is equal to, we got ratio L by D, previously we got 1. Now by using this S and L by D, we are calculating the coefficient of friction variable. Now S is equal to 0.12. Now if you see the figure, S is equal to 0.12. See, this is 0.1, 0.12 somewhere you will get here. If you go like this, and another thing we have to see L by D curve. This is L by D curve. L by D is equal to 1 second curve. Go like this until it touches the second curve. So once it touches the second curve, come towards left side, then we will get the, that is coefficient of friction variable. So we will get coefficient of friction variable is 3.4. See here, see 0.12 somewhere you will get here. Move upward direction until it touches L by D 1. Then you come like this. So somewhere you will get above 3, in between 3 to 4. Therefore, we are going to take, that is coefficient of friction variable is equal to 3.4. So that can be written as mu divided by xi is equal to 3.4. In the figure only we can write that is equal to mu divided by xi. So therefore, mu by xi is equal to 3.4. So xi in the previous step you have calculated. Now we can be able to calculate the coefficient of friction. Mu will get 3.06 into 10 to the power of minus. Once you get mu, substitute here, substitute mu, substitute w, and substitute v. V is nothing but pi dn divided by 60. So therefore we'll get the value of hg. And also here xi is nothing but, since in the first step we got xi is equal to less than 0.001. We should not take this value. We are going to take less than this value. So that's why we are taken here xi is equal to 0.009. And should substitute everything, then we can able to calculate HG, heat generated. Next is heat dissipated. Next formula to calculate heat dissipated HD is equal to CA into TB minus TA. This is the formula we are going to use to calculate HG for the complete design of bearing. Now here C is equal to 11.36 into 10 to the power of minus 3 kilowatt per meter square Kelvin. Again, we are going to convert this into watt per meter square Kelvin. 10 to the power of minus 3, 10 to the power of 3 get cancelled. So we'll get 11.36 watt per meter square Kelvin. And A is equal to 25 dl. We know the value of D, we know the value of L. Substitute, then we'll get area 1 meter square. Again here, we don't know bearing temperature, we don't know ambient temperature. So in order to calculate that, we are going to assume the ambient temperature. To calculate bearing temperature, that is nothing but TB minus TA. We are assuming ambient temperature TA is equal to 25 degrees Celsius. And sure. Now once you get TA, use the formula TB minus TA is equal to T0 minus TA divided by 2. Now T0 is 65 operating temperature minus TA, just now we are assumed 25 divided by 2. We will get TB minus TA. Substitute everything here. C, substitute C, substitute area, and substitute TB minus TA. Then we will get the HT. Now see, the amount of heat generated is 5.512. The amount of heat dissipated is 227. Therefore, we require the amount of heat to be removed, Hg minus Hg. This amount of heat to be removed. Therefore, hence artificial cooling is required. So in this way, we are going to calculate heat generated and heat dissipated, and we have to check whether the artificial cooling is required or not. Next is minimum film thickness and its location. Next unknown we are going to calculate. Previously I told her how to calculate minimum film thickness. See, minimum film thickness is represented by H minimum. This H minimum, sure, we will get by using the formula. The formula to calculate H minimum is delta is equal to 2H minimum by C. So here C is nothing but diametrical clearance, that is equal to xi into D. Xi you know, D you know, you will calculate C. But again there is a two unknowns. One is delta, another one is H minimum. So now our aim is to calculate H minimum. To calculate H minimum, we are going to calculate delta. To calculate delta, we are going to refer the figure number 24.13a. If you see the figure number 24.13a, figure number 24.13a. In the x-axis, we are having S. Number of curves is L by D, and in y-axis, we are having delta. Now, already in the previous step, you have calculated S, and you know L by D is equal to 1. See, now in the previous step, we got S is equal to 0.125. So, Summerfield bearing characteristic number you have calculated. So, therefore, somewhere you will get 0.125, move upward until it touches one curve. So, this is the one curve. So, L by D we got 1. So, until it touches one curve, then come towards the left side, then we will get the value of delta. It is minimum oil film thickness variable. So, we got delta is equal to 0.4 for full job. Once you get delta, substitute in this formula, calculate H minimum. H minimum film thickness is equal to 3.6 into 10 to the power of minus 3 meters. So in this way, we are going to calculate minimum film thickness. Same for the previous problem also. Next, and its location. Now we are going to calculate pi. From the figure number 24.11a, go to the figure number 24.11a. This is the position of minimum oil film thickness, 24.11. Here also same, x-axis is S, curve is L by D. So same thing. So here we are having 0.125. We got S is 0.125, and curve is 1. Move like this until it touches the curve. Then come towards left side. So we will get pi is equal to 50. Position, that is location. So you can see here pi is equal to 50 or 50. And show position of minimum film thickness pi. So in this way, you can calculate minimum film thickness and its location. So to calculate minimum film thickness, we are going to refer this formula. In this formula, two unknowns, one is delta, another one is C. This delta can be calculated by using this figure, and then we can calculate H minimum. And its location is from the figure 24.11a based upon S and L by D. This is the fourth step. Sixth step, and the seventh step is oil flow rate and end leakage. This is the last step. So the formula to calculate oil flow rate is capital Q is equal to, this is the formula, capital Q is equal to lambda Q C square N dash L divided by 4 into psi. Here there are unknown, that is nothing but lambda Q. That is nothing but flow variable. This is the unknown. To calculate flow rate, the unknown is nothing but flow variable. This lambda Q can be calculated by using the figure number 24.37. Now if you move to the figure number 24.37, see figure number 24.37, here x-axis is S, and again number of curves is there, that is nothing but L by D. On the y-axis, we are having lambda Q. Now we know S is equal to 0.125. So I will select this is the curve as 0.125. I will move until it touches L by D1. So now it is touching here. Now if you come towards the left side, then we will get the lambda. See, we are getting lambda Q in between 4 and 5. So we got lambda Q is equal to 4 point. In between 4 and 5 we are getting. So we are going to see some here we will get. So here we will get, that is nothing but 4.3 lambda Q. Once you get lambda Q, substitute lambda Q, substitute C, N dash L, everything, then we will get, we can able to calculate the flow rate. Flow rate is over. Next we are going to calculate end leakage. The formula to calculate end leakage is represented by QS. And sure. Now here we are going to calculate QS. Now again to calculate end leakage QS, we are going to refer the figure number 24.39. If you go to the figure number 24.39, see 24.39, oil flow rate QS by Q versus bearing. Again in the y-axis we are having QS by Q, x-axis is S, and curve is L by D. Again same thing here, S is equal to 0.12. Here and this is the curve for L by D1. So move like this until it touches L by D1, then come towards the left side. Then we will, that is in between 0.6 and 0.7, we can take 0.65. You should see there, here they are taken 0.66 or 65. Therefore, so here you can see QS by Q is nothing but 0.66 or 65. So therefore, QS by Q is equal to 0.66. Now in the previous step, we got Q cross multiplied. That is nothing but 2.5 into 10 to the power of minus 5 into 0.66. Then we can able to calculate the end leakage. So in this way, we are going to calculate oil flow rate and the end leakage Q and QS by using the figure 24.37 and by using the figure 24.3. And last step, power loss due to friction. The formula to calculate power loss in mu is equal to mu W V. Substitute mu, substitute W, substitute V, and we will get the power loss. First step. So totally 8 steps we are going to calculate for the complete design of bearing used for the particular application. Now here we are designing the bearing used for the low speed steam engine. We are calculated the type of the oil, which type of oil we can use. We have calculated the dimension. We have calculated how much amount of heat is generated, how much amount of heat is coming out, whether the artificial cooling is required or not, and we have calculated minimum film thickness and oil flow rate if there is any end leakage or complete, and finally we have calculated the power loss. So this is complete design of bearing used for particular application for 15 marks. Understood. Same procedure we are going for different application for next remaining 2 to 3 problems. So next problem, design the main bearing of a steam turbine that runs at 1800 rpm. Now we are going to design a bearing which is used for steam turbines that is running at 1800 rpm. The load on the bearing is 2500 Newton. So type of the application they are given is steam turbine. Speed is equal to small n is equal to 1800, W is equal to 2500. Now first, based upon the application they are given, we have to note down all the parameters. Now we have to go to the table number 24.2. Now if you see the table number 24.2, see this is the figure table number 24.2. Now here in the first step we have to see where there is steam engine. So in the question they have given application as steam turbine, use it for steam turbine. See where we will get steam turbine. See where we will get automobile, aircraft, main steam engines, locomotives, pumps. Still here we are having railway cars, steam turbines, generators, motors, centrifugal pumps. So this is the here we are having steam turbine. Now for this steam turbine, next we are told that we have to go for mine. Next, so this is the Tmax 0.69 to 1.87. So this is Xi 0.001, and this is L by D ratio, and this is viscosity neta 2.16 into 10 to the power of minus 3, and this is S double dash 241.8. So like now we are going to take application for steam turbine. So we have to note down everything. So we have to note down P, Xi, L by D, neta, and S double dash. Once you get this, remaining is same procedure. So first we are going to take this. So here we can take pressure 0.69 to 1.87. Any value we can take. In between this we can take any value. So I am going to take P is equal to 1 MPa. convert 1 into 10 to the power of 6 Newton per meter. Then again L by D 1 to 2. So in between this I can take any value. I can take 1 or 1.2, 1.52, any value I can take. So I can take L by D is equal to 1. So therefore we know the formula P is equal to W by L into the substitute P, substitute W, where L by D is equal to 1, L is equal to, therefore L is equal to D, then calculate D. Once you get D, substitute here, then we will get here. So since L is equal to D, the value of L and D will be same. Sure. Now if you again resubstitute this in this formula, W, L and D, you will get same value as P. Sure. So next is selection of oil. Third step. Now we are assuming the operating temperature and taking neta is 2 to 16 into 10 to the power of minus 3. You can take any value from 2 to 16. So I am taking 16 into 10 to the power of minus 3 as then we are going to find out the oil, name of the oil by using the figure 24.2. So remaining is same procedure. We are going to calculate all the unknowns up to 8th step. And so it is now we are designing for the steam turbine. So taking the first step is very important here.